Yes.
Thanks. Right, so we have the angular momentum of a particle. Right, so what we're going to look at is everything to do with the angular momentum of a particle, right? So what we saw on Tuesday was the linear momentum, right? So suppose we have our 3D system, right? So we have X, Y, and Z like that. And then we've got, let's say that this is the path that our particle is traveling on, right? Let's say that the particle is referred to by this point P, right? Then from the point O, we know that we can define a position vector, right? So if this is point O, fixed coordinate system, we define this position vector like this, right? And then we also know that tangent to the path, we have the velocity, but we looked at it last time, multiply that by the mass, and you get the linear momentum, right? This is the linear momentum, right? So now if you extend this position vector out and you say that the angle that it forms with this linear momentum, the tangent, let's say that that angle is equal to phi, like that, right? You can define a quantity. So just to complete things, that's L like that, right? So what I was saying was that you can define a quantity called the angular momentum, which is basically a vector as well. And all it is a cross product of the position vector R crossed with your linear momentum, right? Or you can write this as R crossed with L like that, right? And what that means is that you're going to end up with a vector that is perpendicular to the plane that contains R and V, right? So best way to draw that is, let's say, something like that, right? And then you're calling this H naught like that, right? Okay, so this is the moment of momentum, right? So basically you're taking the moment of the momentum, right? So that's the definition of the angular momentum. So it's the moment of momentum of the particle about the point O, right? And clearly, you know, my drawing skills are terrible, but it is perpendicular to the plane containing your position vector R and your linear momentum mv, right? So clearly, you know, since we have a cross product, you can write it in your that rule that we use to find out the cross product by hand, right? So we said that H naught is equal to, you know, you have I, J, K, like that. You got X, Y, Z, and then you got MVX, MVY, and MVZ, like that, right? And if you're looking at it just from the angle perspective, right? So you've got your path. Let's look at it in 2 dimensions, right? So now we're looking at the plane that contains R and L. So you got the point O, right? You define it, position vector like that, right? And let's say that you have an angle for a horizontal reference, theta, like that, and then you've got your velocity vector multiplied by the mass, so that gives you the linear momentum, right? And then this will have two components dependent upon this angle phi, right? So you'll have your mv, as we'd seen, subscript r, right? Along with, in reference to our polar coordinates, right? Then you have the mv theta, right? In reference to this angle theta that is changing, right? So you can basically simplify this expression when you're only looking at the scalar quantities to be equal to r times m times v times sine of this angle phi, like that, right? Or when you're writing it out, when you're writing the scalar quantity out, this is what your angular momentum will be. And we know that this v sine theta is nothing but r mv theta over there, right? Because that's the component that you're finding, which is in relation to this angle theta. Now remember, your phi over here, but this is also equal to mv theta, right? Because that's the perpendicular direction to this position vector over here. And this quantity over here, we know that this is equal to r times theta dot, right? So this simplifies as being equal to m times r squared times theta dot squared, like that. So this is the expression for your angular, the scalar quantity of your angular momentum. All right? Any questions? Do you guys get that? Any questions, guys? No? Easy peasy? All right. Let's keep going. Then you can take the derivative of the angular momentum with respect to time and something interesting happens. So taking the derivative of angular momentum respect to time, say that that is equal to r. We know that the angular momentum is equal to r crossed with mv, right? So if we take the derivative with respect to time, right, now we're going to do it the grown-up way, right? So it says h naught dot, like that, right? And then the dot, you use your chain rule. So you get r dot crossed with mv plus r crossed with m v dot, like that, right? So chain rule applies to the cross of the cross product as well. So now if we take a look at what's happening inside over here, you see that what is r dot? What is the rate of change of the position with respect to time, the vector?
Velocity.
Velocity, right? So this is just going to be equal to v, right? And then for your v dot, what is that?
Acceleration.
That's the acceleration. Absolutely, right? So what you end up with is v crossed with mv, right? And we know that a vector crossed with itself is equal to what?
One.
Nope. Vector crossed with itself is going to equal 0, right? Because the there's no plane that contains both of those vectors, right? So the magnitude of that comes out to be 0. Or if you look at the sine of the angle in between them, sine of theta, that's equal to 0, right? So vector crossed with itself is equal to 0. And then all you're left with is r crossed with ma, like that. All right. Okay. So basically, the rate of change of angular momentum is equal to r crossed with ma, right? And what is ma from Newton's second law?
Force.
Force.
All of the sum of all the forces, the external forces that are acting on your body, right? And what is r crossed with all the forces?
Moment.
Moment. So like the moment, right? The angular momentum is measured about a point, that is that subscript that you're seeing over here, right? So when I was saying H naught, I should have been saying H subscript O, but shortcuts, we say H naught. So the moment, the rate of change of angular momentum about any point is equal to the sum of all the moments due to all the external forces that are acting about that point. All right. So let's write that sentence out as a statement. So sum of moments about O of the forces acting on the body is equal to the rate of change of the angular momentum of the particle about O. All right, so that's the statement of angular momentum. So we've defined what the angular momentum is, right? It's R crossed with your linear momentum, right? And then we've seen that the rate of change of angular momentum is basically equal to the sum of moments about that point. All right, those are the main two takeaways. So any questions till now, guys? Does it make sense? Good? All right. So next, we're looking at conservation of angular momentum. Right, and this conservation only applies when you have what's known as a central force. So let's define those things. So again, if you have 3 dimensions, say x, y, z, you've got some path that your particle is traveling on, right? You've got your point O like that, then there's some point P, right? You've got a position vector that joins O to P, right? Now you've got some force which is directed towards the point O, and that is what the central force means. So let's draw it in blue, some force like that, right? So the conservation of angular momentum only applies when the only force that is acting on a particle is directed towards or away from, it can also be in the opposite direction, from a fixed point. The particle is said to be moving under a certain, under a central force. All right, so what that means is that sum of moments, which is equal to the rate of change of angular momentum, is going to equal 0. Why? Because the moment about the point O of any force that's pointed towards O is going to equal 0, right? So that means that your angular momentum about that point O will not change with respect to time. So what that means is that R crossed with mv is equal to, this angular momentum, which is going to be a constant, right? So let's refer that as equation number 4. All right. So another way to look at it is, again, let's go into 2 dimensions. So you've got your path, right? You've got point O about which you have, the forces acting along this line, right? Your particle basically moves from, let's say, position P naught initially, to another position P like that, right? So you can define your position vector to P naught, let's call that R naught, and then you can define another position vector to P, let's call that R, right? At this point, at P naught, you'll have your linear momentum and V naught like that, right? And you'll have this initial angle phi naught like that, right? So let me draw it another color. Phi naught like that, right? And then you'll have another angle tangent to that part. So MV has changed. And now at this random location, the angle is equal to phi, right? So you can straight away say that when you're just looking, the angular momentum is constant, so the magnitude will also be constant, right? So you can say that the magnitude, which is equal to, initially was just R naught times M V naught times sine of phi naught. Now that is equal to R MV times sine phi, right? So angular momentum in both those positions, even the magnitude is the same, right? So this is constant, right? So now if you go back and write it using your rate of change of the angle theta, now remember, this is where the abstract concepts are coming in, right? So theta is how R changes, like that, right? So you'll see that if I just bring the M over, I get H naught over M is basically equal to, when I look into this expression over here, well, I wrote that wrong. It should be mr squared theta, not theta naught squared. All right, so it's just theta naught, right? Because we know v theta is just equal to r times theta dot. R becomes squared because you have 2 r terms, and then you're just left with the 1 theta dot term in there, right? So that is equal to which color? R squared times theta dot, right? And this is equal to a constant, right? Because H naught is constant, M is constant, so H naught over M is also equal to constant. So this value here, right? So H naught over M, we refer to as using the symbol small h, right? And because we are conserving the angular momentum with respect to the fact that we only have one central force, we don't need to, it's obvious that that angular momentum per unit mass is being taken about that point. So we usually drop that subscript over here, right? So this is equal to r squared times theta dot, right? And that is equal to your angular momentum per unit mass, right? And when we are solving problems, we can straight away just use this expression when we have a central force. And we'll take a look at that when we are when we take a look at our problems today. All right, so guys, questions, concerns? Does everything make sense so far?
I'm sorry, what's H?
Small h or big H?
Small H.
Small h is your angular momentum divided by the mass of the body. So it's your angular momentum per unit mass, right? So all you've done is your big H naught is equal to R naught M V naught sine phi naught, but we'd seen that it's also equal to R squared times theta dot, right? Which theta is the rate of change of your position vector. Nothing to do with this angle phi over here, right? It just works out like that because when you look at the components of your velocity, it can be related back to this angle phi. All right. And then you just left with this term R squared times theta dot, right? So although these two quantities, R might change and theta dot might change, this product for a condition where your body has a central force will always stay constant, right? And that is what your conservation of angular momentum is. All right. Great. All right. So now,
will this be on the test next week?
Do you want it to be?
No, I can't remember if you said it was going to be or not.
No, it's not on the test. This is not on the exam. You're only looking up to what we did till last class in the exam. So homeworks 2 and 3.
All right, thank you. Just double checking.
Yep. No, this will be on the next exam. All right. So now let's look at the predecessor to what's known as Kepler's law. We're not going to go into Kepler's law in our class, but it's really interesting, and I recommend that you guys look it up, right? So suppose you've got your body, which is moving from the point P, let's say, to P prime, right? And we know that there's a central force and everything, right? So before we go on, right? So where do you think this concept of central forces is like super obvious and super applicable?
Gravity.
Gravity, right? Whenever you're looking at gravity, whenever you're looking at celestial objects, you're always looking at the central forces, right? Because that's the Newton's law of gravitation. We're going to take a look at that, right? So this conservation of angular momentum really comes into play a lot when you're looking at Newton's law of gravitation or celestial bodies or orbital mechanics and things like that, right? So that's where we're not formally going through Kepler's law, but this is basically where it comes from. All right, so let's say you're at, space these points too wide apart. So you're in your path, right? You have a central force. You move to the point P prime. You start off at the point P, right? You've got your point O. So there's always a central force, even when you're at P or at P prime, that's pointing towards O, right? Let's give you guys a reference as well to a horizontal for the angle theta, right? So now, if I take a look at that, right? So that is R, and I've moved infinitesimally to a nice position to P prime, right? Where this clearly super exaggerating things, just bear with me. This angle is theta, and then we move a little bit, right? This change in angle, let's say, is d theta, right? And we said that this position is R, and you've changed a little bit. It's, it may change a little bit, right? So if we're looking at this area that's swept by this particle, it can be approximated for really, really small movements by this perpendicular, by this triangle over here, right? So let's say that you've moved on to this triangle over here, right? So what's happening here is that the radius OP sweeps a small infinitesimal area. Right? And this whole area we can approximate with this triangle, right? So that's just going to equal half times the base r times this height here, which we can approximate as being equal to r times d theta, right? Think of arc of a circle. So this becomes equal to half times r squared d theta, right? So next, when we're looking at Kepler's law, what we look at is the areal velocity. So you take the derivative of your infinitesimally small area with respect to time, right? And for this infinitesimal change, we're considering that the position, that the distance r stays constant, right? So the only thing that you worry about is the change in the angle theta, right? So d theta over dt, right? So we know this becomes equal to half r squared times theta dot, right? Where theta dot is your angular velocity. So this multiplied by half r squared gives you a quantity which is called the areal, oh, come on, the areal velocity, right? Let's say that is expression number 6. But now, when we're looking at celestial bodies, right, you're always under a certain force, right? So for a body under a central force, right, we saw that the angular momentum per unit mass was constant, right? So the small h, which is equal to r squared times theta naught, is equal to a constant. So what does that mean? That means that whenever a particle moves under a central force, its areal velocity is constant. And this is in essence Kepler's law, but we're not in orbital mechanics class, and today is probably going to be the only time that we're looking at something close to orbital mechanics. So what I'm going to do is I'm going to send you guys the link to Kepler's laws of planetary motion. You guys can take a look at this on your own. All right, awesome. Okay. All right. So we've set it up, we've set everything up for central forces, but we said that it's valid for orbital mechanics. Why? Well, before we move on, does everything make sense so far? You guys have any questions? All good? Good? All right. So where the big ask, right? The central forces coming into the picture. So they come into the picture when you're looking at Newton's law of gravitation. Right? So I'm sure you guys have seen this before. You've got some particle with a mass capital M. You've got another particle with a mass small m. Due to their masses, there is going to exist a force which acts along the line that joins both of those points or particles, right? And that force F, right? Let's say that the distance between the particles is r, then the Newton's law of gravitation is basically states that force F is equal to gmm over r squared, like that, right? And this is a central force, right? So in this expression here, this capital G is the constant, it's what's known as the constant of gravitation. Which is equal to 66.73 times 10 to the minus 12 meter cubed per kilogram second squared, right? Or if you're using American units, 34.4 times 10 to the negative 9 feet to the power 4 times pound second to the power 4. All right, so if you are a particle of mass m on Earth's surface, right, the weight is equal to the mass of the particle, small m, times the mass of the Earth times the gravitational constant divided by the radius of the Earth squared, like that, right? So this is your constant g, the gravity, which we keep talking about. So that's mg over r squared, right? So here, m is the mass of the Earth, and r is the radius of the Earth, right? So that's the distance between you and the center of the second big particle, which is the Earth. Right, and that, when you do all the math, comes out to be approximately what we know to be 9.81 meters per second squared, like that. All right. All right, next, to complete things, and this is extraneous stuff. You might see some of these concepts while you're looking at the problems, but you're not, no direct questions, right? So when you're looking at a trajectory of a particle under a central force, that's where these space mechanics concepts become more and more concrete, right? So you're looking at the trajectory of a particle under a central force, right? So let's say that you have your path like that, right? You have your point O, that's where your bigger body is potentially. And then you've got some point where your particle is, right? And then we know that you have the central force of gravitation, which is pulling you towards the point O, right? And we can draw a reference point and say that there's an angle theta, and then we can draw our coordinate frame saying that it's ER and E theta, like that, right? And we know from looking at the stuff on Tuesday and the stuff that we saw last week that your MAR, which is equal to M times R double dot minus R theta dot squared, is equal to the forces in that direction, and that's just equal to this F force, but it's negative, right? Because it's in the opposite direction to the unit vector. So that's just equal to the magnitude minus F, like that. Let's give this a number. Let's say that this is expression number 8, right? And you get, for the other term, that MA theta is equal to mass times R theta double dot plus 2 R naught theta dot is going to equal what? What are the forces that are acting in the E theta direction?
There's none.
There's none. So what is going to be equal to? 0, right? There's no forces in your theta direction, right? And now we know from our conservation of angular momentum that the quantity R scopes, Sorry about that. Oh, come on, PowerPoint. R squared times theta dot, which is equal to h, is equal to constant, right? Then you can simplify this expression, well, not simplify, but manipulate it to say that r squared times d theta over dt is equal to h. Or you can say that your d theta over dt is equal to h over r squared, right? And remember, this quantity h is a constant, right? So now what we can do is we can start our mathematical juggling, right? So we can say that r dot is equal to dr over dt. That can be written as dr over d theta times d theta over dt, right? Or plugging in from here, r dot is just equal to h over r squared times dr over d theta. All right. So now when we're looking at these trajectories, life becomes easy if we define another quantity. So now we define another quantity, which is small lowercase u, small u, and let's say that that is equal to 1 over r, right? So when we take the derivative, we see that du over dr is going to equal minus 1 over r squared, right? So that means is that dr over r squared is basically equal to minus du, right? Or if you want to be pure about it, it's the differential of minus the differential of 1 over r. Right? So now if we go back and look at this dr over d theta expression over here, what we can write it as is we can say that r dot is equal to minus h times, now this r squared goes away, right? Because dr over r squared we've seen is just minus d of 1 over r, right? So it's just minus h times the d theta remains, right? So you have d over d theta of 1 over r. Does that make sense? Good, right? Just pure mathematical juggling to get to a trajectory which we can define easily. That's all we're doing right now, right? Okay, and then we can say that r double dot, which is just the dr dot over dt. So you do the same thing, you get dr dot over d theta times d theta over dt, right? And you do the same thing, and then all of this, you replace your h over r squared over here, so you get h over r squared times dr dot over d theta like that. And we can replace that with the double derivative now. So you get minus h squared over r squared by plugging it in again, right? You're just doing it twice now, of d squared over d theta squared times, or not times, but of 1 over r, like that, right? So now what we do is you go back to this expression here, these equations of motion, not the equations of motion, but these Newton's second law equations that we've written up here in terms of AR and A theta, and you plug in for your R dot and R double dot, and also use this quantity U that we define, and what you end up with. Let me know when you guys are done with the notes and on this page. Good?
Can I just have one more second?
Sure.
I'm good.
Many thanks. All right. So now what we do is we, as we said, we substitute what we found. How do you spell substitute? T-I substitute, like that, right? So substitute R dot and R double dot in the expressions we wrote in 8, right? The second one actually, not the one, the first one actually, the one that had the force, right? And you're using the quantity lowercase u that you define. The expression that you end up with is d squared u over d theta squared plus u is equal to f divided by m times h squared times u squared. Right, and this expression over here is the trajectory of a particle under a central force. Right, so this describes the orbits that you see when you see satellites which come in and do the slingshot maneuvers, right? Hyperbolas and parabolas, all of that is described using this differential equation over here, right? So how does that tie in, right? So if you look at space mechanics, right, all that you're doing is just going back to Newton's law of gravitation and just replacing that for your force. Right, so that means is that in this expression, your F is equal to GMM over R squared, like that, right? And when you're looking at space mechanics, you know, especially for if you're considering, let's say you're considering satellites around the Earth, right? Or you're looking at things that have to slingshot around the Earth, right? So that is whatever space vehicle you're looking at, right? So that's the mass of the space vehicle. That is the mass of the Earth. And this distance r is the distance of the vehicle from the center of the Earth. Right, so if you plug it into your trajectory equation, right, so the trajectory becomes d squared u over d theta squared plus u, whoops, plus u is equal to gmm over r squared times m times h squared times u squared, right? And we defined u to be equal to 1 over r, right? So basically u squared times r squared is going to cancel each other out. So mass cancels, r squared, u squared cancels, right? So the expression that you end up with is d squared u over d theta squared plus u is equal to gm over h squared, right? And this term on the right-hand side, we know for a central force is a constant, right? So it has basically nothing to do with, you know, you've taken out the mass of the object completely from your trajectory, right? And that's the interesting thing. All right, how you guys doing? Make sense? So now when you're actually looking to find your trajectories, right, you have to solve this differential equation, right? So when you solve this differential equation, the solution, the general solution looks of the form that U, which is equal to 1 over R, is equal to GM over 8 squared times 1 plus, now there's this new quantity epsilon times cosine theta, like that, right? Where this epsilon is equal to C8 squared over GM. And the question is, what is the C term, right? That just is an integration constant, which changes the kind of, basically, that's what dictates what kind of path you're going to have, right? And this epsilon here is what's known as the eccentricity, right? And depending upon the value of the eccentricity, the trajectory can be an ellipse, right? Ellipse, and that's usually, you know, when you say for those, when you see those circular orbits, right? It's basically what that means is that the mass of the central body is so big that it's not moving relative to the other one, right? So the ellipse becomes a simpler form of a circle, but if you look at it exactly, it'll always be an ellipse, or it can be a parabola, right? Or it can be a hyperbola. Right? Okay. So with that, what I'll do is, you know, if you go to your notes online, you'll see that there is additional notes on, come on, space mechanics, which basically tells you under what conditions you get an ellipse, a parabola, or a hyperbola, right? It's basically the value of your eccentricity, right? And you guys can read this. This is all extra stuff. You have some interesting concepts which come into the picture, right? Not directly going to ever test you on these, but some of these concepts may be in some problems that we look at. All right, everything is on Brightspace. All right, guys, questions, concerns, comments? The main thing from today's lecture, you know, you can keep the space mechanics stuff, the trajectory and all that stuff in the back of your pocket, but the main concepts to take away are angular momentum and the conservation of angular momentum under a central force, when your body is acting under a central force. All right? Okay.